The following program is brought to you by Caltech.
I'll move on to the final talk, which will be by Heather Knutson, who's an assistant professor of planetary science, and she's going to talk about exploring planets outside the solar system.
So I have the challenging task of trying to wrap up after a full afternoon in which you guys have heard some of very exciting results which kind of vary in their focus from the microscopically small, the geology and the structure of rocks on Mars, to the unimaginably vast, so looking at the existence of planets outside our own solar system and trying to place our solar system into that sort of more general context. And so perhaps fittingly, as the last speaker of the day, I'm going to spend my time focusing on that big picture view which exoplanets offer us. So they offer us the chance to answer questions like whether or not our solar system is unique or common in the universe, questions like whether or not Earth-like planets are common in the universe, and perhaps eventually to answer the question of whether or not life is common in the universe. So I'm obviously not going to answer those questions today, but I hope that I will give you a glimpse of sort of where we are on that path, some of the questions that we're asking right now, and sort of some of the interesting clues that are beginning to emerge from these observations that we're making. So just to start out with a little bit of context, for those of you who don't spend all day thinking about extrasolar planets, you might wonder how we even know that they're there to begin with. So this is just an image of the night sky taken with a small telescope. The majority of the points of light in this image are stars. Many of them are like the sun. And so it's certainly not a new idea that these stars, some of them, might have planets which are like the planets in our own solar system. But until recently, the million-dollar question was, if these stars have planets, how can we know that those planets are there? So one obvious answer is that we just need to take a really, really high-resolution picture of one of these stars, and that then next to that star, we might see a smaller point of light, which is the planet. So although that has been done for a handful of planets, it turns out that that's actually a really difficult thing to do. And so the majority of planets that we know of today were not detected using this technique. It turns out that there's actually a really wonderful shortcut to get around the challenges involved in this approach. And that shortcut basically involves taking advantage of an accident of geometry. So for a subset of the planets orbiting nearby stars, they will align fortuitously so that we see the planet actually pass in front of the star once every orbit. So even though we can't actually image the star with the planet moving across the disk, as we did for the transit of Venus, we can measure the brightness of the star as a function of time. So if we're looking at a field of stars, we can measure the brightness of each one of them individually and watch. And what we're looking for is stars which have small periodic dips in brightness. So that dip is caused when the planet crosses the star and it blocks a small fraction of the star's light. So stars which show these small periodic dipping signals are acting as sort of a blinking light telling us, look here for planets. So the most successful planet hunting mission to date has been the Kepler telescope, which was launched in 2009. And it spent the last 4 years searching for new transiting planets in a small region of the sky. Well, small is a relative term. This is a 100 square degree field of view, which is large in astronomical terms. But you can see it here relative to this constellation Cygnus that is actually a relatively small sort of postage stamp on the sky. And so what Kepler did was just to stare continuously at this patch of sky for those 4 years and look for these little periodic dips. So here is sort of the headline result that Kepler found. So Kepler was tremendously successful in finding planets. We call them actually planet candidates because we think a small fraction of them might be other astronomical phenomena which mimic this signal. But we think most of them are probably real planets. And so you can plot up a histogram showing what the frequency of planets is versus their size. And so this is a really interesting thing to look at because this starts to answer the question that I raised at the beginning of my talk, which is how common are planets like the planets in our solar system, and in particular, how common are Earth-like planets relative to other kinds of planets. So you can see immediately that there's this interesting rise which happens. So giant planets like Jupiter are relatively rare. Only a few % of stars have those planets. And this is corrected now to account for the fraction that aren't eclipsing. So as you move down in size, Neptunes get to be a little bit more common. But then there's this big jump that happens somewhere in between the size of Neptune and the Earth. And I think this is one of the most interesting results to come out of Kepler. Because if you think about the planets in our solar system, we don't have anything in this size range. So this region here represents an entirely new class of planets for which we have no solar system analogs. And these planets actually make up the majority of planets which have been detected by the Kepler telescope. So one other noteworthy feature of this plot, and many of you may not have noticed this, is actually if you look at this axis, so this is the fraction of stars with a planet in that size range, but you'll notice that there's this caveat, which is that this plot is only made for planets with orbits less than 85 days. So just for comparison, Mercury orbits the sun in approximately 89 days. So this picture of extrasolar planets, if we were to put the solar system on this plot, it wouldn't even register. None of the solar system planets would have been included. So in a way, this tells you about sort of, the limitations of where we are now. We're really good at finding planets that are very close into their star. So even though Kepler has found many Earth-sized planets, the majority of these planets are so close to their star that they're perhaps more analogous to Mercury. They're really, really hot planets, which may not even be able to hold on to much of an atmosphere at all in some cases. But nonetheless, some of them in this sort of intermediate range still offer an exciting opportunity to study this new class of planets. And so for the rest of my talk, I'm going to focus in on this region because I think this is really the frontiers of where exoplanetary science is right now. With our current telescopes, there's not a lot we can do with Earth's other than to say the planet is there, it's approximately the size of Earth. But we are sensitive enough to learn something more about the properties of these intermediate-sized planets. And so that offers us the opportunity to answer the question, what are these planets? So the first step to answering that question is to figure out, in a very rough sense, what the planets might be made of. And the way that we can do that is by combining two different techniques. One technique, I mentioned before, we look at the eclipse when the planet passes in front of the star. So the depth of that eclipse tells us the radius of the planet relative to the radius of the star. If we observe the same system with a telescope like Keck, we can actually measure an entirely different kind of signal. So as the planet orbits the star, it tugs the star back and forth ever so slightly in its orbit. And if we look at that star with Keck, we can actually measure the Doppler shift of the star's light as it moves towards us and away from us. And that very small Doppler shift tells us that there's something there which is affecting the star. The size of the Doppler shift, the amplitude actually tells us the mass of the object which is doing the perturbing. So if we measure the planet mass and the planet radius, we can combine those together to estimate the average density of the planet. And so that immediately allows us to make a rough categorization. So if the planet has a very low density, it's probably mostly hydrogen and helium, perhaps similar to Jupiter. If it has a very high density, it's most likely something which is largely a mix of rock and iron, more analogous to the Earth. So this is all of the planets today for which we have both kinds of measurements. You'll notice that there's about 200 points on this plot, so this is only a small fraction of all of the planets and planet candidates we know of. But for this small fraction of planets where we have these two measurements, we can see that there's sort of a broad trend on this plot. So here I'm showing you planet mass on the x-axis in units of Earth masses, and planet radius on the y-axis in units of Earth radii. So up here on the right, the majority of planets for which we have this kind of measurement have masses and radii which are similar to that of Jupiter. And so if we calculate their average densities, not surprisingly, we find that they have relatively low densities consistent with a composition which is mostly hydrogen and helium. So those seem to be fairly analogous to Jupiter in our own solar system. As we move down in size, we start to get into the regime of planets which have masses similar to that of Neptune. The exo-Neptunes that we find seem to have slightly higher average densities than the exo-Jupiters, which suggests that they probably have some sort of larger rock or ice core with a thick mantle of hydrogen and helium on top, something very similar to the structure of Neptune in our own solar system. But the really interesting region actually comes down here. And so you'll notice that these are these super-Earths that I was alluding to earlier. So these are things which are bigger than the Earth, but still much smaller than Neptune. And so these planets are the planets for which we would really like to get some idea of what their compositions might be. And so I'm just going to zoom in here a little bit closer into this region so we can look at what's going on. So here now, the x-axis is still mass, but it only goes from 1 out to about 15 times the mass of the Earth. So Neptune would be out over here on the right. And then radius on the y-axis goes from 0 to 5 times the radius of the Earth. And the Earth would be down here on the lower left side of the plot. So there's about a dozen objects in this range where we have masses and radii. And what I've done here is to actually overplot curves which show you if you assume that the planet has a given composition, I can tell you at a certain mass what its radius will be. So if you had a planet which was pure rock, if it had a mass of 10 times the mass of the Earth, it would have a radius just a bit less than 2 times the mass of the Earth. If you instead had a planet which was pure water, it would be up here, it would be a little bit puffier at the same mass. And these planets up here almost certainly must have some relatively large amount of hydrogen and helium, relatively large. They, by mass, doesn't have to be very much, but they definitely have a thick atmosphere of hydrogen and helium in order to be above all of these lines. So if we zoom in on the center of the plot, this is really kind of the unknown territory here, because these are the planets that are kind of intermediate between the different lines that I've drawn. And for these planets, there's sort of an additional complication, which is that we don't know whether or not the planet has a thick atmosphere. And so as I hinted up here, if you take a planet which is mostly rock by mass, and then you dump a little bit of hydrogen and helium on top, you can puff up the radius by quite a bit without changing the mass by very much. So with that sort of combination of rock and gas, you could come up with a planet which has the same average density as a planet which is almost entirely made of water. So in this regime, there is a trade-off between the 3 different sort of ingredients that you have to make planets: water, hydrogen and helium, and rock. And you can imagine having different combinations of those 3 things, which produces a planet of a given mass and radius. So for these planets, just knowing the mass and radius isn't enough to tell us their composition. And so to answer this sort of question of what kinds of planets are these. So just to sort of dwell on this a little bit more, I think it's a little bit less strange to imagine something like this kind of planet here. This would be something which looks sort of like a mini Neptune, if you can imagine taking Neptune and shrinking it down and maybe getting rid of some of the gas envelope on top. There really is nothing in the solar system that looks like this scenario on the left. And so, this is something which we would call a water world. And so when I say water world, you might picture something much like the movie from the 90s, something which is just a planet with this vast ocean. We can debate whether or not there might be dolphins on the water worlds, but it turns out that these particular planets probably don't look like this. So these planets are much more massive than the Earth. They're also a bit hotter than the Earth. And so those 2 things conspired together to mean that they wouldn't actually have a liquid water ocean at the surface. So these particular super-Earths that I'm showing in this region here probably have a thick steam atmosphere, which transitions to a supercritical liquid in the deeper atmosphere. And so there's no actual just sort of, gas atmosphere, liquid ocean surface beneath it. So it's kind of a weird thing to think about, but it's neat to ask if those kinds of planets actually exist. So if we want to break this degeneracy between these 3 sort of potential ingredients, we need to measure the atmospheric composition of these planets. And we can only do that for planets which orbit very bright, very nearby stars. So of all the planets on the plot, there are only 3 here for which we can obtain this kind of data. So how do we actually measure the atmospheric composition of an extrasolar planet? So we take advantage of the fact that these planets eclipse their parent stars, and we make a similar kind of measurement to what I was describing before. We watch during eclipse when the planet passes in front of the star. But this time, instead of just looking at a single wavelength, we look at many different wavelengths. And the reason that's important is that if this planet has an atmosphere, that atmosphere will be opaque at some wavelengths and transparent at others. So the amount of light the planet blocks will vary depending on the wavelength of light that we observe. And so just to show you what that would look like in practice, here's a plot showing wavelength on the x-axis and the relative depth of the eclipse on the y-axis. So high up means more absorption, low down means less absorption. And this is for planet which has the same mass but has been envisioned with a variety of different atmospheres. So on the top, these three sets of lines are for planets which have a hydrogen-rich atmosphere. And so you can see that their spectra have absorption features from water, CO2, perhaps a little bit of ammonia depending on the temperature of the planet, methane. But an interesting thing happens when you take the hydrogen out of the atmosphere. So you can see that for a pure water atmosphere, or sort of Venus-like carbon dioxide atmosphere, that these nice up and down variations are almost completely removed. And the reason for that has to do with this sort of cartoon drawing that I've shown here. So in effect, there's some little ring of the atmosphere which is giving you all of these variations. And the thickness of that ring is very sensitive to the mean molecular weight of the atmosphere. So for an atmosphere which is mostly hydrogen and helium, it's relatively puffy, and you get a relatively thick ring that does the absorbing, and so you get large variations. For a planet which has a hydrogen-poor atmosphere, the atmosphere is much more dense and compact, so the size of that ring becomes much smaller, and you get something which looks much flatter. So what we would like to do right now for these super-Earths is to make this measurement and to ask, do we see large variations with radius that tell us the planet has a thick hydrogen-helium atmosphere? Or do we see small variations with radius that tell us that it might be something more like a steam or carbon dioxide atmosphere? So we make these measurements right now primarily with the Hubble Space Telescope. And so here's an example of an observation that we made just this past year. And in fact, it was even published just this past month in Nature. So this is an observation of a Neptune-sized exoplanet. And so for a Neptune-sized planet like this one, we would expect that it would have a thick hydrogen-helium atmosphere. So it should have a nice, strong, big variation with wavelength that should be really easy to detect with Hubble. So here is our data in black compared to this default sort of hydrogen-rich model in red. And you can see that the signal that we saw was very different than what we expected to see. And so we really had to think quite carefully about why it might be different. So one possible explanation is that we were wrong, that this planet doesn't have a lot of hydrogen in its atmosphere, that instead it has less than half of the mass of the atmosphere is hydrogen. So if you take out the hydrogen, you can make it flat. But you'll notice there's another model on here, which is a third scenario that we came up with. So this third scenario is kind of interesting, but also very frustrating. If this planet had a layer of high clouds, those clouds could effectively make the atmosphere opaque and block this absorption signal, even if the planet had a very hydrogen-rich atmosphere. So just to sort of go back to the cartoon here, if you imagine putting clouds in, they make the whole planet look the same no matter what wavelength you look at. So you can kind of mimic the same signal. If this planet has clouds, they're very different than the clouds that we have on the Earth. At the pressures and temperatures in this planet's atmosphere, the clouds are probably made of something like zinc sulfide or potassium chloride, which would be something like a salt. So that's kind of fun to think about. Some of the hotter exoplanets we study might even have liquid rock or iron clouds, which is also interesting to think about. OK, the very last thing I want to show you today is an observation which is so new we have not even written the paper yet. But I was working on the spectrum yesterday. I got really excited about it, so I decided to put it in my talk. So this is data that was taken with the Hubble telescope of a super-Earth, so something which is about 8 times the mass of the Earth. The data were taken in December and January of this year, so I just got them very recently. And so we're making the same kind of measurement for this planet, and we're trying to answer the question if this is a water world or something more like a hydrogen-rich mini Neptune. So here's what the data look like. So wavelength on the x-axis, transit depth on the y-axis. Here's our hydrogen-rich model in red with a nice big variation. So this is actually a water absorption band here. And then here's our water world model, which looks much flatter in blue. So it's a smaller planet. It's a harder signal to measure. So our data are noisier than the previous example that I showed you. But I think it's still certainly suggestive that they don't seem to be going up and down as much as this red model here. And so the very sort of preliminary results that we're getting out of this is that this planet seems to have a flatter spectrum, which is more consistent with the sort of hydrogen-poor, maybe water world type scenario. And the caveat there is that it may, in this case, be our old nemesis clouds reappearing. And so we don't know yet which of those cases it is. OK, looking ahead to the sort of near-term future, relatively near-term, if we want to do this for other super-Earths and really flesh out our picture of what this population of planets look like, we need to find many more of these planets, which are eclipsing relatively nearby bright stars. The mission that will do that is TESS. It will be launched in 2017. It's going to survey the entire sky, and it's going to find the closest transiting planets to the Earth. Right after TESS launches, the James Webb Space Telescope will launch. The James Webb Space Telescope is the successor to Hubble and Spitzer, which are the telescopes we currently use to measure these wavelength-dependent transit depths. So James Webb Space Telescope will give us a big boost. It has a much bigger mirror. It's much more sensitive, so that we can push down these studies to even smaller and cooler planets that are perhaps more analogous to the Earth. So today we've seen a broad range of topics discussed. So ultimately, the endeavor that we're sort of working on is to understand, you start with this nebula of gas and dust. From it, you form planets. We've mapped out the planets in our own solar system. We think we know them relatively well, although as you heard today, we're still learning new things about Mars, about the outer edges of the solar system, and about even the gas giant planets we know and love. But what extrasolar planets are doing is they're helping us to fill in the bigger statistical picture that gives us a context for our own solar system. So the answer to, is our solar system common or rare, is ultimately a question about how planets form and how they migrate after they've formed. So we can sort of condense this endeavor that we're undertaking into a couple of key questions, which is, how do planets actually form? Is it this bottom-up scenario that Dave described? You have a core and then you pile gas on top. Is it differentiating? How does the location in which a planet forms affect its properties, its composition? What kinds of planets are possible? Do these water worlds, super-Earths, really exist? And ultimately, to answer the question of whether or not there are other planets which look, to the extent that we can determine, like the Earth, that are small, that have a largely rocky composition, that are cool enough to have liquid water on the surface. And so this is something that I think we're just beginning to glimpse the answer to, but we'll certainly get there within the next decade, I think. All right, thank you.